At the Los Alamos Scientific Laboratory in New Mexico, a method has been developed to monitor personnel exposed to the possible intake of gamma-emitting materials and to study the retention and excretion of radioactive isotopes by the body. These men are removing the end plates from the shield of a liquid scintillation counter. It is large enough to contain a man and sensitive enough to detect even the minute amounts of his natural gamma radioactivity. A cross-section diagram illustrates the operation of the counter inside its shield. Gamma rays from the subject strike a toluene solution, causing scintillations. These flashes are detected by banks of photomultiplier tubes and transmitted to analyzing circuits. A normal man weighing 154 pounds emits approximately 400 gamma rays per second due to the naturally radioactive element potassium in his body. The counter itself is a steel tank, 72 inches long and 30 inches in diameter, containing 140 gallons of scintillator solution. The solution is reagent-grade toluene with small quantities of terphenyl plus pop-up. This chemical shifts the wavelength of the light to match the response of the photomultiplier tubes. 108 of these tubes are mounted in 12 rows in the outer wall of the tank. This large number is necessary to provide uniform coverage of the solution so that the scintillations are detected with the same efficiency regardless of where they occur in the tank. The photomultipliers observe the solution through glass windows at the bottoms of the mounting sleeves. Light falling on the photocathode causes the emission of photoelectrons. Multiplier electrodes in the tube amplify the signal by a factor of nearly 1,000,000. The photomultipliers are connected together so that a single pulse is obtained. This represents the total scintillation light as seen by all the tubes. The combined pulse is then sent to conventional pulse heightened circuits, which sort out the pulses according to the energy of the event which produced them. A high voltage control and distribution panel provides a means of controlling the voltage of each photomultiplier individually. By observing the pulses from the counter on an oscilloscope, faulty tubes can be detected. It is possible with this control panel to test the tubes individually and to balance the entire complement of 108 in less than 2 hours. The entire detector is housed in a lead shield with a wall thickness of 5 inches and a weight of 20 tons. The shield serves to reduce radiations from the natural radioactivity of the building, from cosmic radiation, or from other sources. The cavity of the detector can accommodate persons up to 260 pounds and up to 76 inches tall, as well as large samples of foodstuffs. The extreme sensitivity of the counter is due principally to this large sample size. A canvas sling in the loading chute conveys the subject into the counter. From the weight of the subject, one can estimate the normal radioactivity to be expected from the subject's potassium. The average person contains about 130 grams of this essential element, which is naturally radioactive. Measurement of the total potassium content of the body by means of its radioactivity is of considerable medical interest, since it is a good index of fat-free or lean body mass. A button gives the subject control over the chute mechanism, should the counter prove too confining. The lead plug at the head of the sling mates with the cylinder and completes the shielding geometry. Decade scalers and a preset timer on the instrument panel record the actual measurements. A counting time of only 2 minutes provides exceedingly accurate results. This very short time span makes possible the examination of as many as 100 human subjects a day. Similar numbers of other samples, such as water and foodstuffs, can also be measured for their natural gamma activity, and extremely minute increases can be detected. This capability is very important for studies of variations in the natural background levels, for the monitoring of reactor waste disposal, and for preliminary tracer surveys at reactor sites. In all these problems, large numbers of samples must be measured whose activity is comparable with natural levels. Measurements are made at such a rapid rate that the processing of data becomes a serious problem. It is necessary to use modern computing machinery to keep pace with the output. Counting results from each subject are transferred daily to punched cards for calculation of radioactivity levels. In the course of only a year's operation, this results in the accumulation of data files large enough to provide definitive cross-sections. Cards can be mechanically sorted for analysis of radioactivity in terms of population distribution, for correlations of activity with age, geography, or time, and for study of numerous other variables. The whole body counter is sensitive enough to make a simultaneous determination of 2 different gamma activities, such as potassium-40 and cesium-137. In terms of speed and accuracy, it is unsurpassed. This capacity for producing data and handling bulk samples with such rapidity promises to have many valuable applications. The use of nuclear power and experimental reactors accentuates the need for monitoring radioactive waste disposal and the study of natural radiation backgrounds. It is also essential to ensure the safety of industrial workers who handle radioactive materials. Despite stringent precautions, exposure is always possible, and a definitive diagnosis is direct measurement. Standards being established today are the basis for tomorrow's progress. Low-level radiation counters have already proved to be valuable tools in an era of atomic development.